Okay, welcome to homework 4 review. Today we're going to be going over capacitors, which are devices that we introduced last week. We talked about capacitance, and then we're also going to introduce resistors and resistance. Um, so we'll go ahead and jump into it. First thing we need to talk about is capacitors and, well, in a circuit. That's actually the way that we're going to be interacting with them this week. So what we will be looking at are some schematic diagrams. And if you, for a capacitor, a schematic diagram is going to look like this. You have two plates and they're connected to a wire. And then this wire can go on and be plugged into a bunch of other stuff. Like you could plug it into other capacitors and connect all of these wires together and make that would actually look more like a battery, make a whole complicated circuit. And you can do these long, circuitous, maze-like diagrams, right? But what we need to know is how our series of, for lack of a better term, how a pair or several capacitors are connected together in order to actually do any mathematical um, computational stuff with the capacitors. Okay, so we have two different ways that we can connect capacitors together. One of them is to connect them in series. In this case, you have two capacitors that are connected by one of their two plates. So the way that this diagram works, right, is that, oh, it's not allowing me to undo that mistake. There we go. Laser pointer, cool. So you have your parallel plate capacitor. This is one capacitor then with two different plates. And notice that there's a wire that is connecting one of the plates of this capacitor to this other capacitor down here. And so this is what is called a series connection. And we would say that these capacitors are connected in series. And most crucially, this means that when I want to sum them together, since they are in series, their total capacitance is going to be uh, less overall. So your capacitance is a measure of how much charge can be stored. In this case, they're going to have the same charge on each of them. So in series, we're going to have the same charge on each capacitor. And you would find that charge by doing a calculation with the voltage is equal to the charge over the capacitance. But what I want to point out here is that in order to actually find what the charge is on the top, we have to know what the total capacitance is. So our other rule that we have for a series connection is that the total capacitance is actually 1 over the total capacitance is equal to 1 over the capacitance for the first guy plus 1 over the capacitance for the second. So if you have, say, C1 and C2, what we need to do is sum their capacitances together to get a total, and then it is the total capacitance here that we plug in to find the charge if we are given, say, the potential that is dropped over them. And that's what your V is on the left-hand side. Okay, the other type of connection that we can have is what's called a parallel connection. And unlike a series connection where the capacitors are connected via one plate like they are here, in a parallel connection, they're going to be connected via two plates. So you might see something like this, where you have one capacitor on the left-hand side and a second capacitor on the right-hand side. And if I connect both plates by connecting the wires that come out of the plates together, regardless of what's going on elsewhere in the circuit, these are now connected in parallel. So we could say establish some other, potential difference, plug this into a battery over here, and go on with the rest of the circuit. But I notice that these two are connected in parallel. And again, it's because they are connected on both plates, not just one. Um, and what is my rule for parallel? In parallel, you would not have the same charge. What you have instead is the same voltage over each of them. And so if I know the potential difference between, say, this point up here, which we'll call point A, and this point down here, which we'll call point B, and by the way that you would usually know the potential difference is because you'd have a battery there. Okay, so if I know that potential difference between those 2 points, I'm going to have the same potential difference over each of them. So that would be the same voltage. And then when I go to do V equals Q over C, if I know, say, C1 and C2, then I can use each C along with the potential difference between A and B in order to find the charge. So now, if I don't happen to know the voltage, then what I need to do is I need to sum the capacitors together. So in that case, since they're connected in parallel, rather than doing 1 over C like we did with the series connection, now our total capacitance is just going to be C1 plus C2. In other words, you gain capacitance in your circuit by connecting several capacitors in parallel. Okay, and I'll just write for completeness here, but we already have the equation V equals Q on C. And great, now I can talk a little bit about how you actually want to approach these circuit problems. So on the homework, I think you only really have one true circuit problem, and we'll go ahead and take a look at it in a second. But I just want to mention that there is a procedure here, and this may be a good opportunity to do a few extra book problems so that you know how to do these capacitor circuit problems, because I obviously I haven't seen the exam. I can't make any guarantees, but you're virtually guaranteed to have to do, a capacitor circuit on the exam at some point. And but they are kind of formulaic, right? They're kind of you're solving these schematic diagrams, and if you can do them, um, then it's a good place to get a point on the exam. So I would recommend doing a few extra circuit problems. But I'm going to go ahead and introduce one of them here. So we have uh, a bunch of capacitors in this circuit, and we have a voltage source. You'll notice that the lines are of different lengths. That's how you know this is a potential difference or a voltage source or a battery. They also give us a plus and minus to tell you that there are terminals on this battery, and they also label it with V to tell you that it is a voltage source. And this battery is connected into a circuit. On the one side, we have a capacitor that's called C1. And on the other side, we have this one that's called C2 and is connected in series to a second. And then, there you go, and that's called C2. And then there's also another capacitor on the outside, which is connected in parallel to these two together. So these two are in series, and then they're connected in parallel to this guy. And then all of that whole square is connected in series to another capacitor down here. So what I just mentioned there, that's analysis of the circuit and how everything is connected. That's all connected there. The analysis of how all these things are connected is important because what we're going to need to do is step through this circuit, sum together all of these capacitances, and then work our way back down. Okay. Now, we have, as we step through the analysis, I just did the analysis, but I'm going to go back through it, of course, and talk through it. Where I like to start, or where you should start probably, is with the actual battery itself. So the battery itself is right here, okay? And that battery is what establishes a potential difference. So we know that there's a positive on the top, a negative on the bottom, and we know that the charge is roughly going to flow from positive to negative. It's not quite, right? Because it's electrons coming out the bottom, and it's not going to charge if you have capacitors. But that's good enough for the way that we're going to speak about them as we're going through this video. Cool. So this potential difference, anything that is connected to the positive and negative that forms a closed loop with this voltage source is going to have that voltage dropped across it. So let's say that my voltage source here is, say, 10 volts. Then since I can form a closed loop over here, that means that everything that's along that loop has a total voltage of 10 volts. So in this case, that means that we would drop 10 volts over this capacitor C1. And we know the capacitance of C1 is given, and I can thus actually just right off the bat, I can solve for the charge for C1. And that will just come from the voltage over 1 is equal to the charge over 1 divided by the capacitance of 1. And you just solve for the charge. That's part A, that's done. Now the difficulty comes in part B, where we have to find the charge on capacitor 2. So my voltage is dropped over everything on the right-hand side. So C1 is kind of isolated on the left-hand side. It makes it very quick and simple to do that calculation, to analyze the charge there, because it just has the full 10 volts dropped across it. On the other hand, we have this other side. Oh, nope. I wanted to draw, not erase. We have this other side with all these capacitors, and there's also 10 volts there total. But the way that that 10 volts is distributed over that side depends on how all of these capacitors are connected to one another and the rules that we have to use. So remember, we have two different rules. When we're in series, we have to do 1 over, and when we are in parallel, we have to just directly add the capacitances together. And that's going to determine how this 10 volts is distributed over the right-hand side. So that's why we have a little bit of work to do here. And as we work through this circuit, we want to start with anything that is directly connected together. So for instance, my starting place is right here. Oh my goodness, I keep erasing. Okay, there we go. I start right here. I see that I have these two capacitors that are connected by one plate. That means that they are in series automatically. So I go ahead and sum them together. Um, since they're in series, we're going to do the 1 over capacitance rule. So they all have the same capacitances, right? But that means that calculation would look something like this. So right here we'd have 1 over C total is equal to 1 over C plus 1 over C. And it's the same C for both because all the capacitors in this problem have the same capacitance. If it weren't, you'd have like a C1 and a C2. Well, we've already had a C1 on the left-hand side, but you call it CA and CB for each capacitor. All right, so we end up with 2 over C, and this, if you solve, you'll get that the total capacitance here is actually C over 2. So we actually end up with a net capacitor. When we sum them together, we end up with a result that has half the capacitance of each of them originally. All right. Now, once we have that, we can see that the red circled section, which has a total capacitance of C on 2, is connected in parallel to this capacitor over here. How do I know that it's in parallel? Because you could redraw your diagram and you could say, since we've put all this together, let's go ahead and redraw that as just one single red capacitor now. That's our net capacitor. And then fill in the rest of the right side of the circuit. We have something like this, okay? I'm kind of leaving some stuff out, but I've just essentially just redrawn this right here. And now you'll see that I've replaced my two capacitors with a single red capacitor. And analyzing this diagram, we now see that these capacitors are connected on both plates, and so they are in parallel. We know the capacitance of this one is C on 2, and the capacitance of this one is still just C. Since they're in parallel, we simply add them together, and that's C over 2 plus C, and that gives you a total capacitance here. C total is equal to C on 2 plus C, which is equal to 3C on 2. So now, just like we did before, we can replace these two capacitors that I have circled in blue here. We can replace them with a single resultant capacitor with capacitance of 3C over 2. And then we could redraw a diagram again and say that single capacitor is now going to be connected in series now to this guy down here. How do I know it's going to be in series with this one that I've just circled in green? Because it's going to be connected on one plate. If you don't see it, again, you can redraw your diagram. So redrawing the blue circled stuff in blue now, we have a resultant capacitor. I'm trying not to flip the slide here because I want to sort of keep it all in view. But now I have a single capacitor that is connected to that green circled capacitor on the bottom. And see how they are connected in series. So now that we have one more series connection, it means that we can do the 1 over C calculation like I've done up here. So what were my capacitances here? I had 3C on 2 for my net blue capacitor there, and then I have just C for that black one. It's just like a regular one from the circuit. And I need to add them together using the inverse rule because they're connected in series. So I'm just going to sort of, let's see, going to want to, I want to redo this calculation. We have 1 on C total is equal to 1 on 3C on 2. What is 1 on 3C on 2? That actually is 2 over 3C. And then you have plus 1 over C. So 2/3 C plus 1, or 2 over 3C plus 1 over C is going to give you 5 on 3C, which is 3C on 5 when we reciprocate it. So our C total is 3C on 5. Okay, why did we want to do all of this calculation? The reason why we want to do this is because, remember, to go all the way back to the beginning of the problem, we knew we had 10 volts that's going to be dropped across this entire right side. I know I'm going to drop 10 volts there, but in order to find out how that 10 volts is distributed, I need to find the total capacitance of that side. Now that I have done that, I can go back through my circuit, and this is why I have all of these diagrams, and why I wanted to keep them all on the same page. I can work back through the circuit using the V equals Q over C equation right here, and also using these rules that when we are connected in series, we have the same charge, and when we are connected in parallel, we have the same voltage. So those are the rules that we're using along with the equation V equals Q on C, and that is how we work our way back through the circuit and find out the charge ultimately on capacitor C2. Okay, so V equals Q on C. Let's go ahead and write that here. V equals Q on C. To start, I can take my total capacitance, plug it in on the bottom of that equation. I can plug in the voltage of 10 volts that I know is being dropped over the right-hand side, and I can solve for the total charge. If I do that, I'll get some Q value. That is the charge for the entire right. Now, this charge isn't the same. Put that in parentheses. This charge is not the same for every capacitor on the right side, the right branch of this circuit. In fact, it's only the charge for these two because they are connected in series, so they have to have the same charge. So the charge that you would find by plugging in the 10 volts for the battery and the net capacitance that we have right here is just the charge on each of these. Now we would use our other rule. We know that ultimately C2 went into this guy and then it went into this one, right? So we want to sort of work our way back through by doing calculations. So once I have this charge, I know the charge on this net capacitor. Now that I know the charge on that net capacitor, I can say, all right, I have parallel capacitors here. So if I know the charge on this net capacitor, I don't necessarily know the charge on these two parallel capacitors, but I can use this charge, the charge on the right side, and this capacitance along with this equation again to get the voltage over that capacitor. Once I have the voltage over this capacitor, that's going to be the same as the voltage through each of these. So these are connected in parallel, which means that they're going to have the same voltages. And so I would do Q equals V on C. Oops. That was supposed to be an erase. Okay. I've done a lot of this out loud, so just to take a second to do an actual calculation here. So I've got V equals Q on C is what we're using. And we're using the charge to the right-hand side and this capacitance. So that would give us the voltage as being Q through the right over 3C on 2. And then that voltage is going to be the same voltage that is dropped over C over 2, over the C on 2 capacitor. And now instead what we want in order to work back to C2 is we now want the charge. So we'd do a second calculation where we'd find the voltage. We can call this the voltage over 3C on 2. 3C on 2, I'm using as sort of the name for this one. And that voltage is also going to be the voltage over this capacitor. So we could then say that the voltage of the 3C on 2 net capacitor is equal to some unknown charge that we're solving for over C on 2. Now we could solve for this charge. This is the charge that is on the net red capacitor here, but remember that these two are connected in series, so they're going to have the same charge, and in fact, this would be the charge. Okay, so this work is a little messy, and this is a kind of a long, complex problem. But what I just wanted to sort of point out is just we're sort of walking through here. Let's do a recap of how we proceed through these circuit diagram problems. The first thing we need to do is sum the capacitances together according to our rules for series and parallel connections. It's either the 1 over C equals 1 over C plus 1 over C, or it's just C total equals C plus C plus C or whatever. So that's step one. You also want to save your diagrams as you're summing together, because ultimately you're going to turn everything into a single capacitor. And then what you're going to want to do is work back up through your diagrams to get to a single capacitor within the original circuit. And the way you work back up is by using the rules that the voltage is the same for any time that you summed two parallel capacitors together. You'd find the voltage to get back through one of them. Or if you had two series capacitors that you summed together, then you need to find the charge, because the charge would be the same over each of them, and that will allow you to work back through up to your original capacitor. And in each case, you're just using V equals Q over C. That's the only thing we're actually using to calculate in the second half of the problem after we've done the total summation and found the equivalent capacitance. Then we work back through just doing V equals Q over C, and those are the only calculations. So it's not very math heavy, but it is sort of logical and maze-like. And if this is your first time encountering it and you're sort of unfamiliar with these rules, I expect that. That's why I would encourage maybe looking at some other examples from the textbook before moving on. Okay, but we are going to move on. And the next problem is actually kind of a higher level problem. This has also been a homework problem for a very long time. And yeah, so in this problem, we have two capacitors that we've hooked up, but they appear to be hooked up in parallel, except we've connected the positive plate and the negative. We've connected the positive plate of one to the negative plate of the other. So it looks like it's parallel because both plates are connected, but because the positive plate on one is connected to the negative plate of the other, we've like flipped them around. It makes for a weird sort of some way that they interact here, okay? So to start off with, they ask about the potential difference between point A and B. First of all, we have the two capacitors like this, and this one is positive and negative, and it's connected to the other one, which is negative and positive. And they're connected by both plates, but notice that we have positive, negative, and negative, positive. And then there's the potential difference that's established over them. Okay, so to start off, they each have a capacitance. This one is C1, and this one is C2. And they give you the capacitances, they give you the voltage, and they ask you for, first of all, for the potential difference between points A and B when the switch is closed. So, and there's two switches that I have not drawn, but they're on the diagram there. But what we need to find, first of all, is the charges that are on each of these before we close the switches. So the charges will come from just a calculation of V equals Q over C. And the V that we're going to use is as for mine, they say that there's a potential difference of 100 volts. So I would be plugging in 100 volts right here. And then I would plug in the capacitances of C1 and then C2. And you'll get two different charges, one for each. and you'll have a Q1 and a Q2. And oh, uh, and okay, so once we've established this, and we find our initial charge on each, the next thing that we want to do is find the net charge. So the net charge is actually, ordinarily you'd have some sort of sum where you'd add them together. But in this case where we have the reversed polarity like we do, since the positive charge here is going to be balanced out by some negative charge on this side, the way you'd find the total charge just for this specific problem is that the total charge is equal to, it'll be like the absolute value of Q1 minus Q2, right? So that's where the negative, the flipping the capacitors around the way that we did, this is where it factors in. So you actually have to subtract the two charges to get the total charge. Once you have that, ultimately the charge is going to be allowed to balance. And in order to find the total potential difference, we just need to do a V equals Q on C. You just have to do this calculation. And just keep in mind that the voltage that we're solving for here now, we want the total voltage between A and B, where this is point A and this is point B. And it's going to be whatever the total charge is, which we will find with this equation, and then we divide that by the equivalent capacitance. So CEQ is what you'll sometimes see for the equivalent capacitance. How do I find the equivalent capacitance? Well, these are connected in parallel. So in parallel, our rule is to just simply add the capacitances together. And so your equivalent capacitance then, I'll write it up on the upper left, your equivalent capacitance is just C1 plus C2. So here's how you find your equivalent capacitance. Here's how you find your total charge. We plug those both in over here, and we will find the voltage dropped. The second part, there's two more parts that each ask you to find a charge over the two capacitors. Well, since they're in parallel, we know they'll have the same voltage. So once I find this voltage, then I just plug it in down here, plugging in C1 and C2 alternatively to find the new charge over each of them. Cool. Okay, so that's it. And that's a kind of a one-off problem because of the weird polarity flip thing. But cool, that's two problems down at least. And the next one, problem number 3, is we're looking at two parallel plates, and they give us the charges, they give us the electric field, and we also have something that is called a dielectric material. So we talked a little bit about parallel plate capacitors last week, but a dielectric material is, just to take a second, a capacitor has parallel plates with an electric field in between them. And because the plates are filled with air, air can only support an electric field of a certain magnitude before air becomes conductive and the electricity jumps from one plate to the other. This is what happens with lightning. Lightning is that the electric field becomes so strong in the air that the air becomes conductive and electricity shoots through the air. So one thing that you can do when you're building a capacitor to get around this constraint is you can fill the space between the plates with something stronger than air. This is what a dielectric material is. And we simply just need an equation for the electric field due to a dielectric. And that equation just happens to come from Gauss's law, where we have an EA is equal to Q enclosed over epsilon naught, right? So this is a very simplified version of Gauss's law, but this is just to say, okay, the electric field times the area that the electric field is piercing, because we have parallel plate capacitor, your electric field is always perpendicular to the area, which makes that a nice calculation on the left-hand side. The whole integral boils down. The only thing that we then need to include when we have a dielectric is we're just going to make our material stronger, right? So we just add, that's actually a kappa on the left-hand side, kappa, not K, but if you use K, you'll probably be all right. Just make sure to remember that that is a dielectric constant that is not the Coulomb's constant, 8.99 times 10 to the 9th. Anyway, this is the only change. This is your entire equation. And for part A, they ask you to calculate the dielectric constant of the material given the electric field, the area, the charge that is stored on the plates, and of course we know epsilon naught. So you just need to solve this equation for kappa. In part B, they ask you to find the charge induced, and there's just an equation here. This is so the dielectric itself has a surface which touches the plates, right? And you actually have an induced charge on the surface, and there's just an equation to calculate it. Your Q induced is just equal to the charge that's on the actual capacitor times 1 minus 1 on kappa. And that comes from the textbook, so that's just an equation that you need. It hopefully was in the notes as well. Okay, moving on. So second half of this homework assignment is going to be on resistors. And just as a quick intro to resistors, so we talked about charge. Charge stores up when you have capacitors. Capacitors, you have two plates, and what happens is electricity is kind of flowing, and then it hits the plates, and the plates have a gap between them, right? So my electricity flows, but then there's nowhere for this charge to go, so you end up with a positive charge, but then this sort of induces, on the other side, a buildup of negative charge, and then there's the flow away of electricity on the other side. Very roughly. Electricity doesn't actually flow with the capacitor because you have this big gap in the middle. So the actual flow of electricity comes into play when we look at resistors. So what is a resistor? Their name actually helps us out. They're going to resist the flow of electricity. So if I have just like a straight wire, I know that there's always going to be a current that is floating through. And what I can do is I can put a material in there that will resist the flow of that current. And it will usually look something like this. That's the symbol that is used in a circuit for a resistor, is just a squiggly line like that. But in truth, what is going on there is you have, say, some sort of cylindrical object like this, and it's made out of metal, and it doesn't want the current to flow through it. And just as we had over here, charge that builds up and a voltage that corresponds to the charge over the capacitor, here we have a current that's flowing, and we have a resistance to the resistor, and the voltage involved with the resistor is equal to I, the size of the current, times the resistance. So in this case, as your resistance goes up, your current goes down. Whereas in this case, when our capacitance went up, our charge went up as well. Okay. One other thing that I'm going to mention, although I don't think we ever actually have to do it, but when you are working through a resistor circuit, such as like the capacitor circuits that we just did, when you're working through a resistor circuit, the rules are flipped because for a capacitor, the voltage is related to the inverse of the capacitance. For resistors, the voltage is related directly to the resistance. So we'd actually switch our rules. That means that for series resistors, we would just strictly add the capacitors together. And for parallel resistors, we actually use the inverse rule to sum the resistances. Again, you don't actually have a homework problem on resistor circuits, but that's important, I think, to mention. And we will have resistor circuits eventually in a more complex sort of setup later on. So at that point, we'll probably go over a basic one as well. Okay, so let's talk a little bit more about the actual construction of resistors. One thing that they're going to ask you to do a whole lot is to do some problems with current density. So typically, now I'm looking at a cross section of a resistor, right? So this thing's like kind of going off all the way over there. Maybe that's not. Let's see if I can make that better. Nope. Oh, oh no. Okay, let me have that back. All right, I got this. I got this. Nailed it. Okay. So you have current that is flowing through this resistor, and it could just look like a tube of metal, or it could look like a wire, like an especially round wire, wide wire. But they're going to ask you about current density. So I know that total, I have through this whole cross section, I would have a current I, but I could also talk about the current density, which is J, And J, the current density, is going to be I over A, where A is the cross-sectional area of the wire. So this is going to give us a few different sort of problems to do. One of them is problem number 4. In problem number 4, they give you a cylindrical wire. You're going to read this graph that gives you the circuit, the current I with respect to R. And first thing is they ask, is the current density uniform? And this is just a yes or no question, so everyone could ask each other if for the answer, right? We want to know if the current density is uniform. So this is your current density. Current density could be a function of R, possibly. But in this case, I see that the current varies directly with R squared. So my current up top is going to be proportional to R squared, and my area on the bottom is actually going to be equal to pi R squared because it's a circle, right? So I'm going to have an R squared on top, and I'm going to have a pi R squared on the bottom. So the important thing for part A is that my R squareds are going to cancel, and thus we just have a constant value of some sort on the right-hand side. And so my current density is in fact uniform because there's no R variable in the final current density. Or sorry, so it is uniform. I said that right. Okay. Then they ask us to find out what the magnitude is of the current density. So for that case, you just need to find then the slope of the current density versus R squared graph. The slope will just be, we'll just go on top, and then you'll have a pi that's left over on the bottom. So your current density will be, the current we can replace, let's start there. We can write a function for the current with the slope of the graph times R squared. And then we know that the area is pi R squared. So putting all of that together then, our current density, which is the current over the area, is going to be equal to the slope times R squared over pi times R squared. And then as promised, our R squareds cancel, and your value for the current density is just that slope over pi. Okay, so that is uniform current density, but as I mentioned, we could have had an R varying, right? And in fact, in the next problem we do. So what happens when we do have an R that, or what happens when we have a current density that varies with R? I'm just going to talk generally how to approach this problem. There are two different ways, two different problems for you to actually do within the problem itself. But what I know is I have my current density is equal to I over A. And in this problem, they're going to give us some current densities, and they are going to ask us to calculate the current itself. So I actually need to solve for the current. So I have I is equal to J times A. And this is going to be a cylindrical wire. It says that somewhere maybe, or they give us a radius. So yeah, there's a cylindrical wire, which means the cross-sectional area is a circle. It is going to be pi r squared. And thus that means that when my current density is a function of R, and I'm multiplying by an area that is a function of R, in order to find the total current, I instead need to look at the current density at each little radius as I move out. And so in general, the way that we can express this with calculus is that the current is equal to the integral of my J of R with respect to the cross-sectional area. How would I define a dA? If this is the first time that you're seeing it, here's the circle that I want to integrate. I'm integrating with respect to R, so I'm integrating this way from the center out, and I'm adding up. And what I'm adding up is I'm adding up each little ring. So that's like a little, the dA is just a little ring with some little thickness, and that's a little piece of area, and we're going to add all of them up. Now, you're not actually going to integrate with respect to area. What is the dA for a circle? If we have a circle that has an area of pi r squared, if the area is pi r squared for a circle, then what is the differential of the area? Well, you just do chain rule on the right-hand side. Derivative of r squared is 2r, and then you have to differentiate on the inside as well. So you end up with 2 pi r dr. So the integral that you need to evaluate for any current density problem where you want to find the current is you need to integrate from 0 out to the radius of the circle, and you're going to integrate some j of r function, and then you need to multiply it by 2 pi r dr. So you integrate, you'll have a 2 pi always that you can pull out front, and then you'll have your j of r function, and then you just need to multiply by that r right there, by this r, and integrate with respect to that little r. Okay, so I'll leave those up to you. If you have any questions, feel free to reach out. And cool. All right, so we're gonna move into problem number 6. And in problem number 6, we have a graph for the electric field inside of this set up by a battery along a resistive rod. So you have like 3 different sections for this rod. And yeah, sections like 1, 2, and 3. And it's gonna go something like this. Okay. So this is the electric field as a function of, this is now x. It's a function of x. So it's actually a function of the length of the rod, going from 0 to L. And what they're going to ask us to do is we're actually asked to find the radii for each of these sections. So the question here is, how does my electric field relate to the area? How does it relate to the charge density and things like that? So what we do know is that the material is the same throughout each of these. So since we have the same material in each of these 3 regions, that means that the current densities would have to follow the same ratio as the electric fields. And we also know that the current must be the same through each of these. So if we are these sections called 1, 2, and 3? I think they are. Yeah, these are called, oh yeah, they label it right here, 1, 2, and 3. Okay, so we know that the current through section 1 has to be equal to the current through section 2, has to be equal to the current through section 3. And we also know from our definition of charge density, wherever that was, oh yeah, the charge density is right there, current over area. So since charge density is current over area, rearranging that equation, we can replace each of these currents with a charge density times an area. So J1A1 is equal to J2A2 is equal to J3A3. Okay, so I'm getting there. Ultimately, I want to relate my electric field from this graph to the cross-sectional areas, where my cross-sectional areas are pi r squareds. So I know I'm going to replace my areas here with pi r squareds. The question is, what do I replace the current densities with? Well, this is actually just going to be with the ratio that we have here. So it'll be the electric field times some constant that would cancel out. But the current density has to be proportional to the electric field. That's the long and the short of it. So the current density has the same ratio that the electric field does. And so you need to read your graph and find each of these electric field values as a ratio of the others, however you'd like to do that. But you just have the ratio for each section 1, 2, and 3. I guess I'll just go ahead and replace that in this equation by calling it just like E1, E2, and E3. And then your area will be pi r squared, but there's a pi in each of them, so you can cancel that out. So we have r1 squared is equal to E2, r2 squared is equal to E3, r3 squared. All right, and so there you go. You can read your electric fields for each section off of the graph, and you can relate it to the radius of each of those sections. And they give you one and ask to find the other 2. Cool. All right, moving on to problem number 7. And problem number 7, we are still dealing with a resistor. Now we're going to take a cable. We have an electrical cable, and it is a bundle of wires. There's 100 or something, and each individual wire has a certain resistance, and we're going to bundle them all together. So we apply the same potential difference across all of them, and that they give us the total current. So I'm given a total current. First thing is they ask me to find the current in each strand. So the I in each will just be equal to the I total that's given over however many you have. I'll just call it N, right? So just that current is going to be distributed over all of them, and then all together, each of them carries a little bit of current. Each strand of wire carries a little bit of current, and all together they give you that total current that's measured. Then they ask you to find the applied potential difference. In that case, you'd have the individual current now that you found right here, and we know the individual resistance is given in the problem. So if I wanted to find the total potential difference, I know that this is V equals IR. For the resistance, I'd plug in the resistance that's given in the problem. That's the resistance of just one strand. And then I also know the current from just one strand from part A. So together you can then find the potential difference across just one of them. In part C, they ask us to find the resistance of the cable. So in this case, we have to go back to our rules for summing resistors. I mentioned how we flip the rules for resistors. These cables are in effect 100 or so parallel resistors. And when I connect resistors in parallel, what I end up with is a decrease in the resistance, right? Because you're giving the electricity more paths to take. That's kind of how I think of it. It's how I remember it. So since the electricity has more paths of taking, you end up with less resistance overall. So for this one, you'd have, 1 over R total is equal to 1 over R1 plus 1 over R2, and so on. Now, obviously, in solving this problem, you do not want to do you don't want to add a hundred or however many terms. So what I would just mention is that you're going to have your number on top will just be however many you have, and the number on the bottom is just the given resistance. So you could also look at this as just N, the number of wires, over the resistance for each. It's a little r, a big R rather. I used a little r up here, but that probably should have been a big R as well. But anyway, you can then solve for the R total, and notably it'll be much less than the resistance of each little piece. Okay, one more problem, problem number 8. And in this problem, we have 2 wires, again, connected in by end to end, so they're connected in series. And they have 2 different lengths, and they give us the resistivity and diameter of one and resistivity and diameter of the other. We have different resistivities, which means it's a different material. And we're going to join them, and they ask us to find, and send a current through them. So they share that current. And they ask us to find the potential difference between points 1 and 2, 2 and 3, and then the rate at which energy is dissipated. Okay, so we have a couple equations that are in play here. The first one is the resistance equation. Given a resistivity, your resistance is equal to rho times L over A. So if I need to build a resistor, I'll get a resistivity for the material. That's just an inherent property of the material that we're using. I have the length of the resistor, and then I have the cross-sectional area. So these are all given, we're given diameter, but the diameter you'll turn into a pi r squared to get the area. So you're given enough for both what's called C and D to generate using this equation an R sub C and an R sub D. Once you have those 2 resistances, then this just becomes a resistor circuit problem. And the de facto setup is that you have C and D, C and D, and all that they give you is the current through both of them. So like my current happens to be 5 amps. It'll be different for everybody. But I'm given a current, Now the current is going to be the same through each of them. So if I want to find the potential difference over each of them, part A is the potential difference over C, because what are my points here? Let me just label these points. This is point 1, and this is point 2, and this is point 3. So when they ask for the potential difference between 1 and 2, you'll notice that that's just the potential difference over C, right? When they ask for the potential difference between 2 and 3, that's just the potential difference over D. Okay, so for each of these, you would just do a V equals IR, where you will have found the resistances of C and D individually up here. On the flip side, or I guess the second two parts, they ask you to find the rate at which energy is dissipated. If you don't remember from physics 1, that's fine. The rate at which energy is dissipated is called power, and we have an equation for that as well. We have several equations, but the one that we need here is just the power is equal to I squared times R. Let me go, yeah, I squared times R. So our potential difference is IR, our power is the potential difference times I, or just I squared times R. Okay, and that is a run through, at least, just sort of talk about setup for the homework. If you have any questions, as always, feel free to shoot me a message on Canvas, and I will get back to those as quickly as possible. If not, have a good week, everybody, and I'll see you next week.